Swayam Prabha. Digital India. Educated India.
Of slip boundary condition in fluid mechanics, and let us just briefly recapitulate what we did. So, we first gave a bit of a perspective or motivation on I mean why we need to investigate on the possibility of slip boundary conditions. Then we discussed about continuum hypothesis and how does it relate to the thermodynamic equilibrium conditions at the fluid solid interface with regard to the boundary condition at the fluid solid interface. Then we assessed the possibility of slip boundary condition for gases, and for gases our general conclusion was that like if the number of collisions or the frequency of collisions between the gas molecules and the solid boundary is sufficiently large, then there is almost a perfect exchange of momentum and energy between the gas molecules and the solid boundary. So, if the solid boundary is at rest, the gas molecules in vicinity of the solid boundary will also come to rest, and that is known as no slip boundary condition. However, if the frequency of collisions is not sufficiently large, then this may not hold true, and the issue of largeness or smallness of the frequency of collision is well parameterized by the non-dimensional number called as the Knudsen number. So, if the Knudsen number, which is the ratio of the molecular mean free path with respect to the characteristic system length scale, if the Knudsen number is larger and larger or it gets larger and larger, that means the molecules traverse a large distance before another collision, that means on an average the number of collisions is less. So, that is the hallmark of a relatively rarefied system. So, now you can, for the same molecular mean free path, that is the for the same level of rarefication, your Knudsen number will actually be larger and larger if the characteristic length scale becomes smaller and smaller. Therefore, if a gas is not very highly rarefied, but is put in a confinement, that equivalent effect can be a strong rarefication in a larger scale system. So, in a smaller scale system the effect of rarefication is magnified because of the reduction in the length scale of the system, and that makes the possibility of infrequent collisions more for gases in a confined system than for gases in a micro or nano confined system than for gases in confinements which are of larger dimensions. So, based on this we discussed about some classification of flow regimes of gases based on the Knudsen number, and we made a remark that the no slip boundary condition holds good so long as the Knudsen number is typically less than the order of 10 to the power minus 3, but again this is just a rough estimate and this is not a hard and fast number. Then we discussed about a model which was introduced by Maxwell, and it is a very classical model known as Maxwell's first order slip model. So, for that we introduced a parameter which is called as tangential momentum accommodation coefficient, and the tangential momentum accommodation coefficient is basically defined as tau I minus tau r, where tau is the tangential momentum, I is the incident and r is the reflected. So, tau I minus tau r in the numerator and tau I minus tau all in the denominator, where the I is for the incident molecules tangent tau I is the tangential momentum of the incident molecules and tau wall is the tangential momentum of the wall. So you can see that this value of sigma is something when is something between 0 to 1, because there are limiting cases of specular reflection. Specular reflection is when tau I is equal to tau r, that is the incident tangential momentum is same as the reflected tangential momentum, and then sigma is equal to 0. On the other hand, for diffuse reflection, the reflected molecules assume the tangential momentum of the wall. So tau r is equal to tau wall, which makes sigma equal to 1. So in reality it is neither fully specular reflection nor fully diffuse reflection, because the relative proportion of these depend on the condition of the surface. So in reality it is neither of these two, but something in between. So keeping that sigma as a parameter, we arrived at a boundary condition which is the Maxwell's slip boundary, first order slip boundary condition, which is the difference in the velocity of gas molecule at one molecular mean free path from the wall with respect to the wall molecules. So that particular boundary condition was augmented later on by Smoluchowski, who introduced the concept of thermal creep, that is, in addition to the velocity slip, you can also have a sort of temperature slip. I mean, it is not a correct term, but just to give you an analogy, a slip due to thermal effects. And so the idea is that because of tangential temperature gradients, there can be a physical slip of gas molecules over the solid boundary, and for that Smoluchowski added a term in the presence of a temperature gradient. This is tangential temperature gradient, not normal temperature gradient, and this term you can see in the last expression of the view graph that is presented. One important point to mention in this context is that you can use this boundary condition provided you know what is the value of the parameter sigma. Now again, this is like a mathematical exercise that you can substitute any value of sigma between 0 to 1 and you can get some sort of behavior of the system. But in reality, how do you get the value of sigma? See, we are converging to a situation when we will realize that it is eventually molecular simulations that can only give us the right picture. So to understand what is the value of sigma, see, sigma is a parameter, it is an upscaled parameter to represent the behavior, but where from we will get the parameter? So for that we have to appeal to molecular simulations, sometimes statistical, sometimes I mean molecular dynamic simulation, depends on the platform at hand and depends on the length scales and other physical scales that are being addressed. But we have to keep in mind that so far as continuum level calculation, sigma is like a fuzzy parameter, but this parameter can actually be obtained from smaller scale simulations, that needs to be carefully understood. Okay. So now we will come now another point that we discussed in the previous lecture is that what is Maxwell's what is Navier's slip boundary condition and how can we fit the Navier's slip boundary condition in the context of Maxwell's first order slip. Then we introduce something called as slip length, and the slip length again for Maxwell's first order slip boundary condition is you can see very clearly 2 minus sigma by sigma into lambda, the expression that is given in the last equation. So in that we are not fully confident with lambda, but you know, I mean, if there is some possibility by which you know the Knudsen number of the system, then you can have an idea about the average molecular mean free path. If you know what is sigma, I mean by some molecular simulation or from some other source of information, then you can treat the problem like a continuum problem with a modification in the boundary condition, so long as the paradigm of continuum is valid. Otherwise, when continuum hypothesis loses its validity altogether, you cannot use the Navier-Stokes boundary equation with whatever boundary condition. Then when continuum hypothesis is valid, just remember this very simple thing, when the continuum hypothesis is not valid, then forget about the Navier-Stokes equation. The Navier-Stokes equation cannot give you the right picture when the continuum hypothesis is not valid. However, it may be possible to develop a strategy by which you can use the Navier-Stokes equation to get some information, provided you make some additions and alterations in the Navier-Stokes equation, but that is beyond the scope of this particular course and we are not going to discuss that. Now, the more interesting issue is about the possibility of slip boundary condition for liquids. This is an interesting issue because of several points. The first and foremost point is that for gases, slip boundary condition is something which may not be very intuitive, but relatively more intuitive than liquids. The reason is that the gases are not as compact as liquids in terms of molecular arrangement. So, if you apply a force and if the gas molecules are located on a solid boundary, then it is much easy to dislodge the molecules from the solid boundary, because the gases are not very compact and there are and the intermolecular force of attraction is not considered to be that strong. On the other hand, liquids are highly compact systems, so they have strong intermolecular forces of attraction. Despite that, is it a possibility